All right, we need to wrap up 12-9 today, so you can get out those notes. We have one last problem to look at. And we are trying to figure out what function would model this data. Now, we could work through the whole process, but I'm going to kind of be trying to be efficient today. We know that this is going to be exponential. First off, because we just looked at an exponential when we ended yesterday, and that's what this entire model example is showing you. And here, if we look at the common differences from 254 to 730, we're adding about 500, a little under. Then from 730 to 215, we're adding under 500. Under 500, I mean, we could look at these specific values, but it's not the same thing. I'm almost certain. If we do those subtractions, we might as well look at a couple of those just to make sure it's not.
It's not. Well, it would be 50. Is it 4 on the first one? And then just 6.
Yeah. So instead, when we're trying to find the exponential ratio, how do we do that? It's right above this, if you can't remember. If we're looking for that ratio, we know a ratio is a comparison of two values through division. Calvin?
It looks about the same, I think.
Well, the 4
Okay, guys, if we do the subtractions, let's do those first. If we check, is it linear? This would be 476.
Yeah.
And 19,215 minus the 18,730. 485.
And then the others are both 480.
And then, you're certain on that?
I'm pretty sure.
Ends in 5. Let's check it. 695. We don't need to take the thousands. Minus 215. 480. 480. Yep. So these are consistent. So we're around 480, but not quite. Not quite consistent. If I wanted to check, is there a common ratio? And by the way, we could look at level 2 to check, is it quadratic? We add 9 there, then we subtract 5, then we add nothing to the change in the change, so that doesn't work. How did we do this ratio yesterday? To go from one value to the next value. I know. I'm still trying to get healthy. Struggle. Every time I cough, like things shift where they are. Yeah.
So if you do like 18,730 over 18,200.
Yeah, take neighboring terms, take the higher term number, not necessarily the higher value, but the higher term number, and set it in division with the lower term number. This gives us, somebody verify this for me because I am not exempt from mistakes. I think we get like 1.026.
Yeah.
Now we gotta try that again for my next set. So check here. Again, take the higher value divided by the lower value. That gets 1.02. If I round, gives me 6. So my next one was 1.026 rounded. And if we try one more to check if we're doing this right, 19,695 divided by 19,215. We get 1.025 if we round. The next set, 20,175 divided by 19,695. 1.0243. So it's getting a little less. We're still right about there. So if we want a function that will best Notice it doesn't say completely accurately. We're just talking best. We're trying to use this for predictive analytics. Actually, interesting situation last night. We were finishing up our taxes to file them away. And funny enough, taxes are really, really easy. Even though I'm a mathematician, my wife has done our taxes for like the past 3 years. Just because she can't like deal with, I'm like, oh, I'll do it next week. And she's like, no, I want to start it now. I'm like, fine, if you want to start it now, do it. Your taxes do predictive mathematics to assume what you're going to make the next year. So they take a function just like this and they say, oh, here's the Hudsons. Here's how long they've been paying taxes, and they keep paying more and more taxes based off their income. So if this is this year, they predict the next year. So my wife had a momentary freak out of like, wait, it says we're going to owe $7,000 next year. Not that we're going to, at the end of tax season, owe $7,000. That means in the year, we'll pay $7,000 in taxes. Not at one time. So she had a momentary like, oh my gosh, where I was like, okay, calm down. This year, we paid a little over $6,000 in taxes. Just taxes. Money that you give away to the government.
Why is it more?
Because we'll make more next year. Like, every year, if you keep this. So they're predicting that we'll keep the same job. We will both continue getting paid more than we got paid the previous year. If their prediction's wrong, then it did not accurately model. But based off the info that they have, they guess that they can predict. That's what we're going to do right here. Based off the info that we have, we're going to make the best prediction that we can. So we find that ratio value, and we got to choose, well, how far do they round out in the ratio value up there? They round out to the hundredths place. So if we round to the hundredths place, well, the first 3 would have given me 1.03. If I want to round out further and be more accurate, what should we take? What do you think we should make as our ratio?
1.025.
Sure, 1.025. If I want to be even closer to these first higher ones, I could go out another decimal place and just say 1.255. Because that'd be between my 1.25 and my 1.26. So that kind of averages out those values. You pick what you think will best model this. So if you predict that actually we might do a little bit better, you might lean towards the 1.026. If you think, I don't know if we're going to keep having as much growth as we've had, you might lean down to the 1.024. You're trying to figure out what you think will best model this data. So then we use that ratio to set up an equation. So you got to remember our exponential form that's the whole complex thing. But what do we really care about from here? A, B, and the X. And we'll deal with H and K if we need to. But how do I determine my A, my B, and my X? Well, especially if you forget, go back up into the previous situation. Our A value, there 12,575, comes from our beginning, our start, our initial. So here in this situation, what was our initial? Always look at your start term, your 0 term, where you originated. So 18,254 times, and we often use parentheses here because we're going to be taking this to a power. Our ratio, whatever we decide on, so if we want to try to be real accurate, we could say 1.0255 to the x, where x is the number of years that this has happened.
Wait, do you remember what the equation was for compound interest?
Yeah.
For whatever reason, I think it looks similar to this.
So compound interest is compounding interest off the money that is now in the account, and every time interest happens, there's more money in the account to start.
So it is an exponential.
So it is an exponential. So it is a modification of this.
Okay.
It actually uses E as its power, which is Euler's number, or Euler's number, depending on who you ask, how they say it. But it's a term in finance. It's another constant that we use in math, just like pi is a constant, e is a constant. But yeah, so it's a manipulation of this.
Isn't that the one in 14.1?
So I'm pretty sure compound interest is that your balance in your account will be the principal times e to the RT. So it would be the principal amount that you started with, your initial. Your compounding factor, the ratio, is the Euler constant raised to the power of whatever your rate is times however long it's been in there, how many terms.
I remember the way we did it. It was like that. Like E was 1 plus some weird number.
1 plus an R.
Yeah, it was like some weird number.
No, it's 1 plus however much more you get. Like the percent.
1 plus the rate.
Yeah, it was like 1 plus some decimal, which would tell you.
the
Yeah,
rate?
which would be the number.
percent.
Decimal
Yeah,
form of the
you can
percent.
compound. Yeah.
So we have an option now. We can either pop over to 14.1 and kind of wrap up that lesson, what you got. Well, I don't know that we'd be able to wrap it up. Or we can look at 12.10, which continues on with this, but all it really does, I'll show you 12.10 real quick. You've already got the 14.1 notes. But the 12.10 notes, all we're doing is solving systems involving the multiple types of functions. So it would be saying, where does this quadratic function meet this linear function? Or where does an exponential, well, there's quadratic and linear again. Yeah, pretty much everything we're doing is quadratic and linear. So this is not too bad. It's just a front-back notes. What? Oh, yeah. Well, you can do the same with like a linear and an exponential, but it's harder. So what do you guys feel? You want to do this, or you want to go back over to 14.1?
I'm going to do 14 because I already have the notes.
I want to do this.
So shut your eyes. If you want to do 12.10, keep running through chapter 12 so that we can finish and shut the door on chapter 12 next week. Raise your hand if you want to do 12.10. Just keep trucking. All right, put them down. If you want to go into 14.1 and deal more with exponentials, raise your hand. You're just feeling really exponential today. All right, well, that was effective. We will go into 12.10.
You said next week, so I just wanted to get it over with.
Yeah, so there are only 12 topics in chapter 12. So we will do this day. We'll probably actually get through this day. And then we'll do 12.11 and 12.12. We'll do some review next week. Because we only have a 4-day week next week. But we'll still be able to get through this, do some review, and take the test. Or at least start the test.
Yeah, that's right.
Yeah, where's the I don't care?
I had such a sway in votes, we did not need to pursue the I don't care option. The I don't care option was off the table. You have to care. So, we have two different mopeds. Any of your friends have mopeds yet? It's like,
my dad has one.
yeah,
I don't have them.
I want one.
I know,
But it's
it's
funny
so
when
fun.
you say, like, my dad has one. Does your dad have one that you can ride when you're 14?
He'll probably
Like,
So
I
some are like, some are
And my friend
motorcycles that look like a moped. Like a Vespa where you ride like this in front versus where you straddle it and ride like this. So when you're 14, you can get a moped. Potentially. Could. Potentially. We've got two different mopeds. Now, why younger people can ride mopeds is mopeds have what's called a governor built into it that governs the amount of speed that you can have. They only have a top speed of like 40 miles an hour. You can't take them on the highway. You can't take them on certain roads. There's a lot of restrictions. So this moped is at its top speed of 40 miles an hour. Now, this moped has been modified, and we've removed the governor, and it will just keep getting faster and faster and faster and faster.
Dang, son.
So its speed is now modeled by distance equals 4.5 times t squared.
Jesus.
Dang.
That's some hardcore modifications right
He has
there.
nothing to do with this, and if you let him take the wheel, it's not a good idea.
I'll let Jesus
So, we want to figure out when does the red scooter catch up to the blue scooter. At the start line, this is the funny thing. We're assuming, like let's say the red scooter is really cocky and they're like, look, I'll give you a head start. You can get your speed, and when you pass me, then I'll start. So this is what the situation is assuming. This scooter's going 40 miles an hour at the start. or 40 whatever it is. It may not be miles an hour. It's probably feet per second. Yeah. So t's seconds. So this is 40 feet per second. This is 4.5 feet per second squared. This scooter's already at speed, at a constant speed. Its speed will not change. This scooter is stopped. So 1/1000. All you had to do was go 40 feet in 1/1000. That's not that fast. We could convert this to a miles per hour if you really want to, but we don't need to right now.
Wait.
This scooter is starting and then catching up and will eventually be going faster. How could we figure out how long it takes for them to be at the same location? Obviously, 0 is a solution. When the time is 0, they're at the start line, but the one scooter's already going. The other scooter has to start. They start at the same place. This guy takes off, and this guy has to speed up. Where do they meet again? It's that age-old problem. If a train leaves here and a train leaves there, when do they meet? But luckily, these are going in the same direction. Those train problems often are going in different directions.
I have a question. Can I try to convert that to miles per hour?
Yeah, if you want to, go ahead.
I'm pretty sure it's
40 feet per
144,000
second in miles per hour.
feet
I'm
per
doing
hour.
this. I'm doing this. I need to know. I want to get number.
What was the whole thing you said for miles per hour? Well, saying you had.
tomatoes.
5 tomatoes.
Yeah.
That's just
Yeah.
per mile.
5 to
That's feet per mile.
Oh, 5 tomatoes.
How do we figure out when these are at the same location? Caleb.
I mean, I guess you could graph it if you really wanted
We
to.
could, but we don't need to. Colin?
Hey, Ethan, I beat you to it. It's
I'm doing it for myself.
27 and 311.
So it's not that fast.
Miles? 27 miles?
You can ride your bike 27 miles an hour. You really can.
Yeah,
Like,
I go like.
I got my dad to ride beside me when I was a kid down a hill, and I was going like 32. Like, he was in his car and I was on my bike. So 27 miles an hour is not that fast, especially on something with a motor. Sure, then we gotta get on with
Okay,
this.
so we had one of those speeding things, the things that like will register and it'll say the car's speeding.
Oh, yeah.
Okay, so me and my dad, we went down because I was playing softball at the time, and I was like pitching at it, and it would tell me how fast it was going, which is really cool. But then we tried, me and my brother were riding our bikes.
Yeah.
Okay, that's my story. I'm done.
I mean, every time I see one of those things, I still, even as a 27-year-old, like, I was up in the hills riding my bike, and I turned around and did it again, because I was like, I wonder if I can go faster. If they're at the same location, their distance that they've traveled has to be equal. So set their distances equal to each other, and let's solve out. So if I have 40t equal to 4.5t squared, what could I do to start solving?
Take the square root.
I don't have both sides squared.
Wait,
If I take the square root of this,
take
it'd be
out
really
t?
confusing. Like what?
Take out t.
I can factor out a t.
I didn't hear you.
I'm sorry. Hear it. If you rose your hand, then
Yeah,
I
right.
could.
Rose his hand.
Stop.
You just got cooked.
If your hand had been raised, I maybe would have viewed it and called on you.
Dab on it.
So now we get 40 equals 4.5t. And to finish solving, we divide by 4.5.
8 8/9 seconds.
8 8/9. And that'll be in seconds. Sorry, that does not say SCC. That's SCC.
So after about 9 seconds.
So then, at any time after 9 seconds, who will be ahead?
The red scooter.
The red scooter, until at some point, if it maybe reaches its top speed, but it is increasing exponentially
There is no top speed.
up until a point. Now, if there is no top speed, eventually he's probably going to crash. But
No light speed.
Hyperspeed.
Yeah, that's
Or-
like the Millennium Falcon.
or he'll end up back in the future.
Oh,
Straight up,
wait.
he's going through
What if he
time.
reaches escape velocity?
I was about to say,
That red
or
scooter is
or
the Millennium Falcon.
he goes back in the future. Back
That's
in time,
only,
or Back
that's
to the
only 80
Future,
miles
or-
per hour. That's weak sauce compared to what he could do.
So-
my mom could drive me.
Yeah, I would not laugh.
Just like in Math 1, when we dealt with linear systems. Remember those linear systems? Hey guys, we gotta have class. We've been off topic enough for today. With linear systems, there was either no solutions if the lines were parallel, one solution if they just had different slopes, and infinitely many solutions
If they're the same line.
if they're the same line, same slope, same intercept. So here, we only have 1, 2, or none. Because if we're dealing with a parabola and a linear function, obviously these are the sort of situations we can see. We can see that essentially our linear function will be tangent to one of the points, easiest if it was like horizontal at the vertex, but it could also be diagonal and just touch tangent at a point, could not touch at all, or it could go straight through it and touch twice. This actually had two solutions, but we don't care about the zero. So if we were to graph this, this would look something like my blue scooter, 40t, my red scooter, and this point right here was that almost 9 seconds, that 8 8/9. So up until then, the red scooter had gone less of a distance until we surpass, and he will exponentially increase that gap. Yep.
Couldn't it also be one solution if it's the line of symmetry, or the axis of
Yeah,
symmetry?
any point that just crosses through once. But a vertical, like if we're talking realistic situations, yeah, I guess that'd be like, what if it said at time of whatever? That would be like your vertical line. So like, what is the solution of the red scooter at time 10 seconds? Then the solution would be how far he had gone. So if we graph these are pretty easy to graph. You can set up some tables if you want, or just think they're okay. 0, -2. So I'm going to call this my blue function. I've got tons of highlighters if you want. And I'll call the other one like my red function or something. If x is 1, what would my y be? If x is what? Here? 1 squared, 1 minus 1 minus 2. So wait, I get the same result from x being 0 as I get with x being 1.
Which means the axis of symmetry is a half.
Love it.
Wait, what?
So when we plugged in 0 here, we got -2. And when we plugged in 1 here, we got -2. Which Calvin quickly identified means my axis of symmetry is between those 2 points. That is the bottom of my parabola. Its vertex is right in here at 1/2. And we don't really care about that, but that's good to like point out and be able to identify. Don't let that throw you off. Some people forget and they switch around their function rule, and they're like, no, that can't happen. Yeah, you can have 2 of the same outputs. You can't have 2 of the same inputs equal the same output. So then at 2 squared minus 2 minus 2.
Yes. Wait, you asking a question?
Yeah, what's the y value of y at 2? 0. Because we have 2 squared minus, like, so 4 minus 2, then minus 2. I'm going to reorient real quick, try to put some of your other points on that graph, please.
Wait, are you recording this?
Yes.
Okay.
You're not all here, so I definitely record when we're not all here.
Wait, who isn't? Oh, is it?
If I move over to my x equaling 3, what would my y equal there?
4.
4. And I will probably be off the chart if I go any further. So I would probably just... Now I will also know that I have symmetric points. I can build the rest of my parabola based off that symmetry. Any questions? Now, model your linear. Well, I see I have a intercept of +2. What's my slope?
-1.
-1. So once I know that, those points should be easy to place. So my solution points here, actually, yeah, let's just put the whole point. So we have -2, 4, and 2, 0. And if this was modeling a real situation, we would interpret those solutions and determine if they're both valid or if only one of them is valid or what that's telling us. Questions? Try the got it on your own. You can always, if you want to use a table in your TI-83, you can use that to spit out values. Do not look up here unless you need help. And when I set up a table, if I set up a table, sometimes my results just jump out at me. So my solution points are at -2, positive, or yeah, -2, +1. But still, we could graph this. So I've got -2, 9, which is off the chart. -1, 3, 0, 1. Crap. -1, 3. Get the right point on the graph. 0, 1, 1, 3. And -1, 7, still off the chart. 0, 5. So one of our solution points is off the graph and we wouldn't be able to see it. So sometimes if we just graph it, we're going to miss one of our solutions, but maybe that solution is extraneous, bless you. But be careful if all you do is graph it. If I had graphed like this, just what I see, I know that I'm going to intersect somewhere up there because my parabola keeps getting higher and my line is straight, so it's got to go through somewhere. So even if you only graphed and saw one solution, you can interpret the graph and say, well, I know there's actually going to be two. Any questions on this? Is this pretty straightforward?
Yeah.
Just an extension of what we did in Math 1. So now, another method that we used that I like a lot is the algebraic process of solving by elimination. Let's just get rid of things. Let's combine the functions together to see what can cancel each other out. So we have pool A and pool B. Pool A's attendance has increased steadily. Pool B rose first and then fell. So, like, they were popular, and then a kid pooped in the pool, and everybody decided to go elsewhere.
Oh, cool.
That's what happens.
Oh, brown.
Which, technically, you're supposed to shut the pool down and drain it. So, we want to solve this by elimination. What do we think could eliminate here?
Just for one poop. You can do all that.
There's
Yes.
poop in the pool, you're supposed to drain it.
Well, I was
It's
at
your
a,
duty.
I was in a wave pool at Kalahari, and a kid pooped in the pool.
I know. Not everywhere does. But you're supposed to.
And puked. Like at the same time.
Ew.
In a pool.
And you stayed in the pool.
No, I had to get out.
Okay, good.
I was in it at the time. I just saw it happen. I didn't see it happen. I just saw it.
All right.
Cleaning it up.
Let's focus. So, I have
Then
39x.
I got back.
So, I have 39x and 28x. I have an x squared in the one function. No x squared in the other function. How could we solve this by elimination? What do you think could eliminate? Right?
Go to the X and the 4.
Get rid of the x and the 4. We got to pick one to work with at a time.
X.
So if you want to get rid of the x's, you got to find a way to get them both to be the same value and then subtract one function from the other, or them to be opposite values and then add the functions together.
I do 4, that's easy.
Yeah, 28 and 39 don't look like they're going to work well together. If I think about factor lists, or not factor lists, product lists, like the multiples of 28 and the multiples of 39, looking for a common multiple, we're going to have to get pretty big to get there. If I think about 4 and 64, can I turn 4 into 64? Yeah. What do I do with it?
6 by 8.
Multiply by 8. 8.
16. I meant 16 and I said 8.
So, this then becomes
It's like,
right?
Shouldn't you multiply it by negative 16 so they cancel out?
So we can either make them the same and subtract one from the other, or make them opposite and then add them together. You're going to end up with the same result in the end. So that's up to you. If you want to use the negative 16, you can. I just keep them both positive, and then I subtract one from the other. How do we do this? Michelle?
Multiply the stuff inside by 16.
Okay.
You get the 28x turns into 448x plus 64.
And we still have that negative x squared, the 39x, and the other 64. So if you kept them both positive, I now take away the bottom function from the top function. So since this was 0x squared, and I'm taking away a negative, I really add, so I get x squared. I'm subtracting these, 409x,
Yeah, but do you have to screw with the Y when you're doing the multiplication?
what do you guys think? What do you remember from Math 1?
You have to do it from both sides, don't you?
Basic logic skills and me screaming at my wall.
So if we did, this would have been 16y and this would have been y.
And then when you subtract it, it comes to 15.
Where do we go from here?
So, well, 'cause don't you have to get rid of a variable on both sides. Yeah.
divide by 15.
Alright, you have X and you don't know what X is.
We divide by 15.
Well, I don't know. That's like that seems like a really bad idea, but
409 divided by 15 is going to be pretty messy.
okay, yeah, that doesn't work. Never mind. Abort.
Abort.
Callahan.
Max exposed Mr. Hudson.
Max, raise your hand.
I'm waiting for you guys. Guys, this is not much of an extension beyond what we did in Math 1. That's why I'm not spoon feeding it to you.
You should probably do that.
No, you're not babies. I'm not spoon feeding. Max, what do you got? Quit sitting on your knowledge.
You should eliminate the y, not the constant.
Why?
That's exactly
Why?
Okay.
Oh,
Now,
so it's
puns aside.
quadratic.
Puns aside. Why?
Then you will only have one variable and then you can solve.
So, if we forget about all this,
Are you kidding? It's quadratic. I wrote that all in.
It's
I
quadratic.
asked you guys what we wanted to do. You told me cancel out the constants.
I was like,
So, if we take a different route, hold up. If we take a different route, and we just subtract b from a, I end up with x squared. Don't erase. Grab post-its. Just right over top. You don't waste your time erasing.
Why don't I can't
39 subtracted from 28 is going to give me a negative 11x and then a negative 60. Now, if we cancel out the y's, what does that equal?
The big
Zero.
And this now is what? A quadratic function. Are there two values that when multiplied will make negative 60 and when added will make negative 11? Or summed, or whatever you want to say. Added or difference. So we know one's got to be negative, one's got to be positive. We're thinking, is this easily factorable? So one will be negative, one will be positive. Megan?
15 and 4.
So, what's your actual solution?
X equals 15 and negative 4.
Negative 4 doesn't matter though,
Oh,
because we're in a realistic situation here.
we are? Oh, we are. Okay.
On day 15,
They had the same attendance.
no, I know. It's like when you're writing it out. The grammar.
Rams are.
Well, if you got like some data at the end though, it's just on day 15, period, then you can do no comment.
Yeah.
Although,
Question.
Count once.
Try.
You skewed them.
Hey, so I'm kind of glad that we did that. The point of elimination is to only work with one variable. So, while that was a little like surprised that it took us that long to realize that we were doing the wrong thing.
Thanks, man.
The point of elimination, I'm surprised that none of the rest of you remember that, is to work only, like if we, and we're going to continue to do this as you go into Math 3, you will work with elimination processes when you have 3 variables to start. And you start by canceling out one of the variables to get a new set of functions that only have 2 variables, and then you use those 2 variable functions to cancel out again and get a set of functions with only 1 variable, or a function with only 1 variable.
Did we already do that with substitution?
Yes. Yeah, working with A, B, and C. Yeah, same thing. So try our got it. Try our got
Now this just seems so much easier.
But now you're going to remember it better. If I had spoon-fed it and just told it to you, it goes in one ear and out the other. When we wasted time and realized that we did the wrong thing, we will remember it better.
We don't waste time here.
We did.
At Phoenix, we don't waste time.
When we did math we didn't need to do. I'll rephrase that. Your brain has an answer?
Yes.
So what do we get here? We end up with 0 equal to minus 10. And then your factored form,
X minus. Oh, right. Am I still going?
Sure, I don't care.
X minus 5, X plus 2.
So your actual solution? And then it actually asks us what then was the attendance. So if their attendance is going to be the same, it's probably easier to plug this into your linear. So we would do 36 times 5, then add 54, and our attendance on day 5 will give us our solution point, 5 to 34.
I have such good maths, and apparently we were supposed to do that on the previous one as well.
Yeah, I just didn't care.
Nice.
Because we know how to sub in. We're fairly good at that.
Debatable. We also couldn't figure out how to do these elimination
But
methods.
now
Yeah,
we'll
but
always
subbing
just
in
go
is
back to
easier.
when max streaks
And you
were
hadn't
so
done this
much
for a while. We hadn't done elimination for a hot minute.
I don't like elimination.
Yeah, elimination's one of those methods where it's like, if it jumps out at you and says, haha, eliminate me, but still, it's not normally the easiest one.
I like
Well,
substitution.
easy's relative. Yeah, substitution always works, no matter what. Sometimes the numbers get a little weird, but it always works.
Like when I see that, I just want to make them equal to each other.
Well, that's not really, it's kind of substitution. So, if we do this with substitution, if we plug in and set these equal to each other, we have x squared minus 6x plus 10 equal to 4 minus x. Since they're both equal to y, we can just set them equal to each other. What do you want to do then? Add an x. Like put in a new x. Add x to each side. So if I do that, I get x squared minus 5x plus 10 equals 4. So we get x squared minus 5x plus 6 equals 0.
It's a quadratic.
It's a quadratic now.
The solution of the factor is x minus 3 times x minus 2, and then x equals positive 3
Boom. And we could plug in, and our solution points will be at 2, 2 and 3, 1
So much easier.
in XY form.
Yeah.
Any preguntas?
We leave it a minute.
I bet that wasn't a question. I bet that you guys will have a fairly easy time with this.
How did you
Dude, I've been watching you the whole class period, and I thought you had enough self-control. You only a ruler. It's plastic. It's breakable. And you were sitting there essentially testing how much can I bend this before it
Sam
breaks.
wrote like 3
So I think your statement of I didn't think that would happen just means I was waiting to see at what point that would happen. And you found that point.
You should have seen Sam broke like 3 of Mr. Hall's rulers in one day.
You owe me a ruler.
Because he broke one.
Now,
and
if you
tried to
never
return
bring
it,
me a
broke it
ruler,
instantly.
obviously nothing's going to happen. But if you want to impress me, like one of those top-notch students, at some point, bring me back a ruler.